Okay, hi. Hello, everyone, and welcome to attend my uh, online presentation. My name is Zili, and I'm currently a PhD candidate at University of Adelaide. I will represent my research group to present at this conference. This presentation is based on our paper of intrinsic fracture energy of 3D print cement mortar obtained from snapback behavior in indirect tensile testing. So firstly, I'd like to introduce the Brazilian disc test. So this test is conducted by applying compression to the disc specimen and generate tensile stresses across the vertical diametric cross-section, and the increasing load eventually causes the specimen abrupt failure. So based on a typical load displacement response, for example, a really brittle behavior was observed and low reaching the peak value and then suddenly drops to zero. And this fracture mode is demonstrated as the mode 1 from opening as shown in the figure. And this GIF image shows the dynamic behavior is usually observed by having multiple fractures, and eventually it will broken with flying fragment. And normally, for the peak tensile strength for disk can be determined by the formula, which is based on peak load, thickness, and the diameter of the sample. Therefore, based on the conventional Brazilian disc test, I will briefly introduce a new technique called OSPID, which it is stand for Adelaide University Snapback Indirect Testing. So for this test, is applied for adding a lateral displacement. So that this LVDT will have a lateral restriction for controlling the lateral deformation, and which the specimen setting, we will have a DRC camera, which can capture the from surface, and we will also put two holder to fix this lateral LVDT for the lateral control. And for this picture, so this one is like a zoom in for how we set up the camera. And normally we have three monitor. So from the left to right, the first one is the MTF's operation. So this computer can directly control the testing machine. And for the middle monitor, is just for recording, like for example, the load displacement and any testing information. And also we have the AE monitoring, which is stand for acoustic emission. So so normally, as we see at the picture here, we will put two acoustic emission sensor to capture some acoustic response, just doing the whole loading process. And for this image at the top, we showing the comparison of a good speckle painting and and a bad one. So in order to get a really good DRC image, we need to satisfy there is a final speckle for the image capturing. Also, I will introduce three common loading condition concept to give you some initial understanding of material failure behavior. So for the first condition, we call snapbacks. If you can see from the figure, the loading is increasing with vertical displacement decreasing. However, the lateral displacement is also decreasing by the time. This means the material is under lateral control to release the excess energy. And then when we look at the second condition, we call it unloaded. So it's like for both vertical and lateral displacement are decreasing, which the indicate loading system just unloaded the specimen. For the last condition is softening. So for both vertical and lateral displacement are both increasing. This scenario indicates the energy dissipated until the fully fracture. So for OSPID, it used indirect lateral expansion from LVDT to control the loading and testing. It allows capturing snapbacks and remove dynamics effect in Brazilian testing. For a specimen with 90-degree loading angle, the loading will be perpendicular to the interface as shown in the top left region of the figure. The strand contour image are captured by the DRC camera, which indicate the strand start concentrate at the middle of the specimen, and the snapback behavior was well captured for 5 to 6 hour duration at the post-peak region. If we go deeper to observe the testing behavior of figure on the top left shows the specimen deformation with DRC contour image under loading. And the figure at the top left shows the evolution of low vertical displacement and lateral displacement versus time. Also, the setup of the specimen was displayed in the bottom right for some better illustration. So when we look at the figure, for the loading stage before reaching the peak load, the vertical displacement increased exponentially. After that, for the post-peak stage, the vertical displacement keeps stable with slightly variation. The reason is that for the lateral displacement increased linearly, which is means the lateral control by this lateral LVDT is under control, and this indicate a better control of the loading, and the cracking progress are continue before some fully fracture after the snapback behavior. So furthermore, I would like to introduce the low and vertical displacement relationship with DRC contour image and the evolution of strand profile, which is shown in this slide. So as we can see, the value pattern in this small photos show which, when we look at the zoom in picture here, so there's no straight cracking path, which was perpendicular to the interface of the specimen. So if we look at the strand profile, which this is the illustration photo, and we can see we will having indicate horizontal line. So from the beginning, from point 1 to point 5, and as you can see, when after the snapback behavior, the specimen will be fully fractured, and the strand will be concentrated in the middle region. And you can see at the central of the specimen, we will get the epsilon XX, which means the horizontal strand will be have a jump, or we can call it a peak in the middle. So, and then I can briefly explain how to obtain tensile strand and mode 1 fracture energy during the whole testing process. And we assume the fully fracture at the end of the location of the snapback behavior, which is the red region, indicate the dissipated energy during the loading process. In addition, this blue region indicate the elastic strand energy stored in these two broken halves. The peak strand can normally be determined by the formula of peak load, diameter, and the thickness. And the mode 1 fracture energy can be determined by the formula of energy dissipated and fracture surface. And for the elastic strand energy was not considered as fracture energy, since it is the energy after the fracture of specimen. And these are some preliminary results of some of my smaller disc specimen with a size of 50 mil diameter. The void effects leads to this variation result due to, as you can see from the picture below, there's some void effect due to some poor printing quality. But at the moment, I'm trying to improve this printing quality because it's from 3D concrete printing. So when we look at for more specific analysis for one specific specimen A, it can, as you can see from the low and vertical displacement graph, it obtain a minor snapback behavior after reaching the peak, but it is not really smooth because you can see some flipping behavior. And as we can see, we mentioned about the AE sensor, so which here it is indicated by this red curve. So, and we have 3 different indicating points. And as you can see, this additional measurement from the acoustic emission indicates some at the beginning until the fully fracture. there's a minor internal fracture was happening until we call it a large sound response for fully fracture. And also the DIC contour can show the result. But recently, some good result can be obtained with a large size specimen with 75 millimeter diameter. So this plot and the video shows a comparison of specimen with well-controlled and uncontrollable. So for the specimen which was uncontrollable, the total release energy is the combination of the fracture energy and kinetic energy. When we look back to the specimen was under control, the blue area we mentioned before indicate the elastic strain energy released after the fully fracture. And further, if we look at the both low displacement pots, both red area indicate the dissipated energy due to cracking gradually. And this area is about 63% by my calculation of the gray area of the total release energy. So the off-speed control of 75 shows the actual fracture behavior and can estimate the fracture energy of 3D print based this specimen. So in conclusion, the indirect displacement control must be used to capture snapback, or we call it class 2 behavior. Moreover, our off-speed seems to be the first for Brazilian disc testing on 3D print cement mortar, and it also works really well with a range of brittle material. Further, the off-speed is capable to remove or minimize the dynamics effect of the Brazilian disc specimen, and it can prolong the fracture timing and to facilitate the use of advanced image-based instrument technique is what we call the DIC correlation. And for some of the single tests I just showing, both strain and mode 1 fracture energy can be obtained. However, some challenges are still remaining for fracture testing on 3D print cement-based material due to their size effect, and also for some poor printing quality. So further investigation will be follow up in this field. And thank you for your attention, and welcome to ask me some question. Yeah, thank you.